We usually imagine a galaxy as the finished thing and the black hole as the dark secret at its centre, a hidden tenant living deep inside a much larger home. James Webb has started to unsettle that picture. In some of the earliest systems we can see, the centre does not look like a late arrival at all. It looks advanced, oversized, almost premature, as if the furnace were already burning before the house around it had fully taken shape. And once you feel what that means, the early universe stops looking like a calm beginning and starts to feel like a place where order was being negotiated in real time. If you enjoy slow, deep stories about how reality turns out to be stranger than our first ideas about it, stay with me here. This one changes the shape of the sky a little. So let's begin with something that feels familiar. Picture a modern city at night from far above. You see the broad spread of neighborhoods, roads, dim edges, and in the middle perhaps a bright downtown core, dense and intense, pulling movement toward it. That is not a bad way to picture a galaxy and its central black hole. The galaxy is the city. The black hole is the concentrated center, small compared with the whole, but powerful enough to shape what happens nearby. For a long time, that image felt stable. Galaxies form, stars gather, structure builds up, and in the middle the black hole grows with the system, sometimes quietly, sometimes violently, but still as part of the same general history. And in the nearby universe, that expectation has good reason behind it. When astronomers look at large galaxies around us, the mass of the central black hole often tracks the properties of the surrounding bulge. Not perfectly, not mechanically, but clearly enough to suggest a long relationship. Over immense time, galaxy and black hole seem to influence one another. The host feeds the center pushes energy back into the host. A kind of uneasy partnership emerges. That picture is important because Webb did not arrive to study a complete mystery. It arrived in a universe where a broad narrative already existed. The early cosmos was supposed to show us rougher versions of the same story, younger drafts of structures we know well, less polished, less massive, less settled, but still understandable. If we looked back far enough, we expected to watch the first neighborhoods appear, then small central engines, then larger galaxies, then the mature relationship we see around us now. Instead, in some cases, Webb is showing us something that feels badly out of sequence. To understand why, we need to place ourselves not in a finished universe, but in one that is still very young. Not young in the casual way we use that word, but young in the bodily sense. Young the way a face is young before its features harden, or a city is young when the streets are still mud and scaffolding. Webb can see systems from only a few 100 million years after the Big Bang. That sounds large because all cosmic times sound large, but on the scale of galaxy history it is startlingly early. We are looking at reality before it had much time to repeat itself, refine itself, or settle into habits. And that is where the problem begins. Because black holes were not supposed to get huge that quickly. A black hole can grow by swallowing gas, dust, stars, or by merging with other black holes. But growth is not simply unlimited. As matter falls inward and heats up, it shines. That radiation pushes outward. There is a natural tension between gravity trying to pull more material in and light pushing some of it back. Under ordinary assumptions, this puts a kind of practical speed limit on how fast a black hole can bulk up. You can feed it aggressively, but not infinitely. There is a rhythm to the process. So when astronomers found very massive black holes in the young universe even before Webb, the discovery was already unsettling. Some early quasars, brilliant beacons powered by matter falling into giant black holes, were visible at times when the universe should have been too young to produce them so comfortably. It was like finding a fully operating industrial port on a coastline that should still be mostly empty. You could explain it, perhaps, but you could not explain it casually. What Webb changed was not just the existence of this tension, it changed its texture. Before Webb, many of the earliest known black holes came from the brightest, most dramatic objects, the cosmic equivalents of lighthouses seen across enormous darkness. That told us something real, but it also left open an escape route. Maybe those were rare extremes. Maybe the strange cases were just the flashy outliers, the exceptional monsters that do not represent the deeper rule. Webb has started closing that escape route, because it is not just finding a few screamingly bright quasars. It is finding a wider, murkier, more intimate population of early objects that suggests black hole growth was not merely possible very early, but common, concealed, and in some systems astonishingly far ahead of the surrounding galaxy. That distinction matters. A few spectacular anomalies can sit at the edge of a theory without breaking it. A population begins to exert pressure everywhere. Part of that pressure comes from the kind of light Webb was built to see. It observes the universe primarily in infrared, which means it can detect light that has been stretched by cosmic expansion during its journey to us. Light that began in the visible or ultraviolet long ago arrives reddened, shifted, softened into wavelengths older telescopes struggle to capture with the same reach. In practice, this makes Webb less like a better camera and more like a tool for seeing through age itself. Not perfectly, not magically, but deeply enough that the first billion years stop being an almost featureless blur. There is a human feeling hidden inside that engineering. When you look at these objects, you are not seeing them as they are. You're seeing messages that left when the universe was still in its opening movement. Not ancient in the museum sense. Ancient in the sense that the structures we now take for granted were still deciding what they wanted to become. That is why sequence matters so much here. If a black hole already looks too large, too active, or too mature at that depth in time, then it is not just an odd object. It is evidence that the script may have been looser than we thought. And once that possibility enters the room, even a faint red point of light starts to feel heavy. Because a dot is not just a dot when it comes from the edge of cosmic dawn. It is a clue about what formed first, what rushed ahead, and what kind of universe could produce a concentrated engine before the larger structure around it fully announced itself. That is where Webb's strangest finds begin to matter, and where the old story starts to lose its clean shape. One of the reasons this story has so much force is that it does not begin with a dramatic photograph of a single impossible object. It begins with a pattern. Webb started turning up a class of early sources that looked small, red, and oddly concentrated. They did not spread their light the way many young star-forming galaxies were expected to. They looked compact, almost self-contained, like distant embers seen through rain. Astronomers began calling them little red dots, which sounds almost gentle until you understand why they became so disruptive. At first glance, a faint red source in the far universe could be many things. Dust can redden light, distance can shift it, dense star formation can complicate the picture. A small galaxy packed with stars might look compact, but as more of these objects appeared, the simple explanations began to strain. In many cases, the light seemed too concentrated, too energetic in the wrong way, too suggestive of something compact and hungry, hidden behind gas and dust. Not merely a young galaxy glowing. A central engine at work. That is the important change in mood. We move from asking whether giant black holes existed early, which we already knew, to asking how many less obvious systems were also hiding active black holes in the young universe. That broadens the problem enormously. It is the difference between finding a few giant towers on a horizon and realizing the whole skyline may be rising earlier than expected under the fog. If many of these little red dots are powered by accreting black holes, then Webb is not just revealing isolated extremes. It is catching a phase of early cosmic life that had been largely invisible to us. A phase where central black holes are growing behind curtains of gas and dust, compact and intense, before the surrounding galaxies have become easy to read. In other words, the center may be announcing itself before the city grid does. And the center, in some of these systems, is not modest. In the nearby universe, the mass of a central black hole is usually a small fraction of the mass of the host galaxy's bulge. Again, not a rigid law, but enough of a pattern that it shaped how astronomers thought about coevolution. Black hole and galaxy grow together over time. They influence one another, but one does not usually appear grotesquely ahead of the other. The proportions feel livable. The skull matches the body. Then Webb helped uncover an early galaxy whose proportions did not feel livable at all. Because through a lucky alignment, nature itself provided a magnifying glass. A more distant object was gravitationally lensed by mass in the foreground, its light bent and brightened on the way to us. This kind of lensing is one of those things that still sounds invented even when you understand it. Space is not just empty distance, it has shape, and mass deforms that shape. If the geometry lines up just right, a remote source can be enlarged, distorted, and made more visible. Not cleanly, not like a perfect instrument, but enough to let us study details we would otherwise miss. What Webb saw in that lens system was deeply unsettling. The central black hole appeared to account for at least a few % of the stellar mass of the host, and perhaps much more depending on how the host is modelled. That may not sound dramatic until you compare it with the local expectation. In mature galaxies around us, the central black hole is usually far less dominant. Here the ratio looked elevated enough to feel not like a normal early draft of the modern relationship, but like a serious imbalance. The core was too heavy, the centre was running ahead, and that phrase matters more than it first seems to. Running ahead is not the same as simply existing early. We already knew black holes could appear early. The growing tension is that some of them do not just show up early. They look overdeveloped relative to their surroundings. They look like a downtown district rising before most of the surrounding streets have been laid out. They look like the engine has been installed while much of the ship is still framework. This is where the title begins to earn itself, not because there is one decisive image showing a black hole floating in pure emptiness before any galaxy exists. That would be too simple, and the universe rarely gives us simplicity when the truth is more interesting. The real revelation is subtler and stronger. Webb is finding systems where the black hole appears ahead in mass, ahead in activity, and ahead in maturity compared with what the visible galaxy seems ready to support. That last part opens another layer, because mass alone is only one clue. Structure matters too. Feeding matters. The way gas moves around a black hole matters. Some early quasars seen by Webb do not just look massive, they look organized. Their central regions already show signs of surprisingly mature accretion structures, as though the machinery of growth is not improvising in chaos, but operating with a confidence that should have taken longer to develop. That does not mean the early universe was calm. It means some black holes were settling into efficient, powerful feeding modes frighteningly fast. Imagine arriving at a shoreline you expect to be nearly empty and finding not just a fire, but a harbour already functioning, cranes moving, ships docking, warehouses lit. You would not only wonder how the port got there, you would wonder how much unseen infrastructure had to exist for that scene to be possible. That is the feeling these systems create. Their visible galaxies often do not seem ready for the weight and organization of what sits at the center. There is a temptation, when hearing this, to picture black holes as exotic villains that somehow break the normal rules. But the deeper truth is more elegant and more unsettling. They are obeying gravity. They are simply revealing that gravity, under the conditions of the young universe, may have built concentration before it built comfort. Centralized power may have emerged before surrounding structure looked complete. That possibility also helps explain why the little red dots matter so much emotionally, not just scientifically. They are faint signs of hidden concentration. They do not present themselves like grand spirals or majestic mature galaxies. They look cramped, veiled, compressed. You have to lean toward them conceptually. And when you do, they suggest a universe in which early growth was often concealed. Not the clean, visible assembly of graceful systems, but something denser and more private. Something happening behind curtains. If you were standing inside one of those young galaxies, it would not feel like living in a finished cosmos. The gas content would be higher, the environment rougher, star formation could be fierce, dust and turbulence would complicate the view, and somewhere in that thick interior, a black hole might already be swallowing matter and blasting radiation into its surroundings, changing the future of the system before the larger shape of the galaxy had stabilized. That is not just an observational puzzle, it is a story about chronology, about cause arriving before the context looks ready for it. And once chronology comes under pressure, every assumption around it has to be retested. Because if the center is too massive, perhaps it started with a larger seed. If it is too active, perhaps it fed above the pace we considered normal. If it is too mature, perhaps the young universe was better at organizing inflow than expected. Or perhaps several of these are true at once. The old staircase from ordinary stars to stellar remnants to gradual black hole growth may still exist. But Webb is making it harder to believe that staircase was the only path available. Somewhere in that realization, the whole early universe changes character. It becomes less like a clean origin story and more like a crowded workshop. Heavy gas clouds, rapid inflows, mergers, radiation pressure, collapse, obscuration, bursts of formation and destruction all happening within spans of time that, on cosmic scales, barely count as an opening movement. And from within that rush, some black holes seem to have emerged not as late consequences, but as early organizers. That raises another question almost immediately. If these giant early black holes were really so extraordinary, then surely they should have lived in the most crowded and favorable neighborhoods imaginable. Surely the richest cosmic real estate would be the only place such things could happen. But even there, Webb found reasons to hesitate. That expectation seems sensible on its face. If you want something to grow very quickly, you imagine giving it every advantage. More gas, more mergers, more nearby structure, more opportunities for matter to pile into the center. In that picture, the earliest giant black holes should mark the densest, busiest neighborhoods in the young cosmos. They should be the downtown cores of the first great urban sprawl. Sometimes they probably were, but not always in the clean way that intuition prefers. Webb and related observations have turned up ancient quasars that appear surprisingly isolated compared with what many astronomers expected. Not utterly alone, not hanging in featureless nothing, but not obviously embedded in the richest swarms of the neighboring galaxies either. That matters because it complicates one of the easiest explanatory moves. If every early monster lived in a crowded region overflowing with fuel and collisions, then the story could remain straightforward. Extreme surroundings make extreme growth. Case closed. But reality seems less cooperative. Some of these black holes may have found ways to grow rapidly even without the most obvious external abundance. That pushes the question inward. Maybe the crucial conditions were not only about having the busiest neighborhood. Maybe they were about the internal state of collapsing gas, the efficiency of inflow, the size of the initial seed, or temporary phases of feeding so intense that a black hole could surge ahead before its host looked impressive from the outside. This is where the phrase "before massive galaxies" becomes interesting in the right way. It does not have to mean that there was literally no galaxy at all, only an orphan black hole somehow floating unsupported. The more scientifically grounded and more provocative possibility is that the black hole reached a mature or overmassive state before the host became what we would recognize as a fully built massive galaxy. The center pulled ahead of the larger structure. The hierarchy formed out of order. That distinction may sound technical, but emotionally it changes everything. We are not talking about a universe that followed the expected sequence a little faster than usual. We are talking about a universe where, in at least some systems, the sequence itself may have bent. You can feel the difference if you translate it into ordinary life. Imagine walking into a new town and finding a towering financial district, all glass and stone and concentrated wealth, but only scattered roads, half-built neighborhoods, and unfinished utilities around it. You would not simply think, this town grew fast. You would think, something about the order of construction here was unusual. The center was prioritized. The rest had to catch up. That is exactly the pressure Webb keeps applying. It is not doing so through one kind of object only. We have the bright early quasars that were already difficult to explain. We have the little red dots, many of which seem to point toward obscured black hole growth in compact early systems. We have cases where the central mass looks too large relative to the host. We have mature-feeling feeding structures appearing at strikingly early times. Each piece on its own invites caution. Together they create a mood that is harder to dismiss. The early universe may have been very good at making concentrated gravitational engines before making galaxies that looked proportionate to them. And that takes us to the real-time problem. Because there are only so many ways to build a giant black hole quickly if you start small. One common route begins with the death of a massive star. The star collapses, leaving behind a black hole with perhaps a few tens of solar masses, or maybe more in special conditions. From there, growth happens through accretion and mergers. But if you run the clock from a small seed forward under ordinary assumptions, some of the early black holes Webb is helping illuminate become deeply uncomfortable. There just does not seem to be enough time to climb from modest beginnings to enormous mass without either feeding very efficiently, beginning from a much heavier seed, or exploiting a growth mode that was once treated as marginal. Think of it in bodily terms. It is not merely that someone gained weight quickly. It is that they gained several lifetimes of growth in what should have been only the first few months. Even before you ask how, you recognize that normal pacing is not enough. That is why astronomers talk so much about seeds in this context. The question is not only how black holes grew, but how large they were when the race began. If the universe started some of them from very heavy seeds, then the clock becomes less punishing. You're no longer forcing a tiny remnant to become a giant almost immediately. You're beginning with something already substantial. This leads into one of the most fascinating possibilities in modern astrophysics: direct collapse. The standard public image of black hole birth is stellar death. A star lives, burns, collapses, and leaves a black hole behind. That route is real. But it may not be the only one that mattered in the earliest chapters of cosmic history. Under the right conditions, a huge cloud of primordial gas might avoid fragmenting into many ordinary stars and instead collapse much more directly, creating a large black hole seed from the outset. No long staircase of stellar generations. No slow accumulation from a tiny remnant. More like a section of the staircase never being built because gravity found an elevator. This is one of those ideas that sounds almost too convenient until you understand why it remains difficult. Gas usually likes to cool, clump, fragment, and form stars. Preventing that requires special circumstances. The cloud must remain hot enough or dynamically arranged enough to avoid breaking into many smaller pieces. Radiation fields, gas flows, chemical simplicity, and local conditions all matter. So direct collapse is not a narrative escape hatch. It is a physically demanding route. But it is exactly the kind of route astronomers revisit when ordinary timing starts to fail. And Webb has made that revisit feel less optional. Partly because it can see farther back into the era when such conditions might have occurred. Partly because it is finding black holes and candidates so early that heavy seeds become much more appealing. And partly because some observations appear to hint at objects that fit the broad spirit of direct collapse expectations. Large early black hole seeds associated with environments that do not look like the aftermath of long, rich stellar histories. That last phrase brings us to something even more delicate than mass or brightness: chemical memory. Stars do not just shine, they alter the universe. Inside stars, lighter elements are fused into heavier ones. When stars die, especially in explosive deaths, those heavier elements are thrown back into surrounding space. Later generations of stars and gas clouds inherit that material. In astronomy, elements heavier than hydrogen and helium are often called metals, even when they are not metals in the everyday sense. The name can sound dry. The reality is not dry at all. These elements are residue, ash, evidence that stars have already lived and died here. So when astronomers examine a distant galaxy and find signs that it is chemically enriched, they are reading history, not complete history, but enough to know that multiple stellar generations have likely come and gone. That matters because a rich stellar history gives time and mechanism for building black holes the slower way. Many stars, some die, black holes form, gas cycles, mergers happen. The usual story has room to breathe. But what if that chemical residue is barely there? Then the room narrows. If the galaxy is near pristine, close to primordial in composition, then it has not had much time for long generations of stars to live, die, and pollute the gas with heavy elements. And if there is still a substantial black hole already active inside such a place, the whole sequence starts to feel unnervingly compressed, not just fast, too direct. That possibility hovered in the background for years as a theoretical longing. Webb has begun to bring it much closer to the center of the discussion, and once it does, the title becomes much more than a catchy inversion. It becomes a serious question about whether some black holes were not merely early guests in growing galaxies, but among the earliest architects of those galaxies' future. A major reason that question now feels so alive is that Webb has not only found active black holes at remarkable distances, it has found at least one case that carries a more intimate kind of evidence, the kind that does not just say something large and energetic existed early, but whispers that the surrounding system may still have been chemically young. That is an entirely different level of discomfort for the old story. Because chemical youth is not just another data point, it is a clock. If you walk into a room and find soot on the walls, warm ash in the fireplace, and the smell of smoke hanging in the air, you know a fire has already burned there, even if you never saw the flames. Heavy elements play a similar role in galaxies. They are signs that stars have lived, died, and returned processed matter to the gas around them. Not instantly, and not all by the same route, but enough that a chemically enriched galaxy tells you history has already been happening inside it. So when astronomers reported a black hole in a galaxy from roughly 700 million years after the Big Bang that appeared near pristine, with strikingly little evidence of prior heavy element enrichment, The meaning of that result went far beyond the object itself. If the interpretation holds, then we're not just looking at a young black hole in a young galaxy. We may be looking at a black hole in an environment that has not lived through the long, busy stellar ancestry the standard route would normally rely on. The usual pile of prior generations, dead stars, leftovers, recycled gas, and gradual build-up seems strangely absent or at least severely reduced. That is where the title begins to press on the mind in a much more literal way. Not before galaxies in the absolute sense of a black hole floating through emptiness, but before the host had become chemically and structurally mature in the way we expected, before massive galaxy growth had left the clear residue it usually should, before the surrounding history looked old enough to justify the thing at the centre. And that is hard to shrug off. Because if the black hole was already there and already active while the galaxy still looked close to primordial, then one of two broad things becomes easier to imagine. Either black hole seeds could begin very large, skipping much of the ordinary climb, or growth in some early systems could proceed with astonishing speed under conditions we still only partly understand. Perhaps both. In either case, the black hole no longer feels like the late beneficiary of a long galactic life. It starts to feel like an early contender for the main event. There is something almost biological about that reversal. We are used to thinking the body forms and the heart develops within it. But in this picture, the pulse is there frighteningly early, driving influence through a structure that is not fully differentiated around it. The centre is not waiting politely for the host to finish becoming itself. The centre may be helping decide what the host will become. That possibility changes how we should picture the young universe. Popular imagination often flattens early cosmic history into a kind of dark simplicity, as if the first few 100 million years were mostly emptiness, with a few scattered lights turning on. In reality, it was dynamic, uneven, chemically evolving, full of collapsing gas, fierce radiation, short-lived stars, and local conditions that could differ dramatically from one region to another. Webb is showing us that these differences may have mattered so much that there was no single clean path from primordial gas to mature galaxy. There may have been multiple routes, some of them far more top-heavy than expected. And once you allow that, the black hole ceases to be a detail hidden in the middle of the story. It becomes one of the forces that may have organized the story from the inside. This is worth slowing down for, because it is easy to lose the emotional weight under the technical terms. When astronomers say a galaxy is metal-poor or chemically pristine, they are not merely classifying it. They are describing how much past has already passed through that place. Hydrogen and helium are the deep starting materials of the cosmos. Heavy elements are later work. They are what happens after stars become furnaces and then spill their insides back into space. To find a substantial black hole in a galaxy that seems to carry little of that later work is to find concentrated power in a place where the usual evidence of long preparation is unusually faint. It is like finding a roaring industrial boiler in a town whose roads are still dirt and whose buildings still smell of fresh wood. Something got ahead of schedule. That does not automatically prove direct collapse, and this is where honesty matters. A near-pristine galaxy can still have complexity. Observations at these distances are difficult. Interpreting spectra is delicate. There may be hidden structure, unseen populations of stars, or models that change as more data arrives. No single result should be turned into theology, but it does something more valuable than theology anyway. It makes older comfort hard to maintain. It takes an idea that was once a theoretical convenience and places it close enough to observation that we can no longer treat it as a distant curiosity. Direct collapse, in that sense, is not just a mechanism. It is an answer to a feeling the data keeps creating. The feeling that some black holes entered the story already too big to have grown from ordinary beginnings within the time available. To appreciate why this matters, it helps to imagine the standard route as a staircase. A massive early star forms, burns briefly, dies, leaves a black hole. Matter falls in. Perhaps it merges with another black hole. More gas accumulates. Over many cycles, if conditions remain favourable, the mass climbs higher and higher. That staircase is real. The trouble is that some Webb-era objects seem to be standing too high on it too soon. So direct collapse asks a different question. What if, in some rare and violent regions of the young universe, gravity did not build a staircase at all? What if a large primordial gas cloud, under the right radiation environment, and with the right suppression of fragmentation, collapsed into a very heavy black hole seed almost in one sweep. Not infinitely fast, not magically, but fast enough to erase much of the timing crisis. Instead of beginning with a seed the mass of a dead star, you begin with something tens of thousands or hundreds of thousands of times more massive. Suddenly the race looks very different. That would not mean the early universe was simple. It would mean it was opportunistic. When conditions lined up, gravity could jump tracks. And that phrase may be one of the quiet revelations running underneath all of Webb's black hole results. The early cosmos was not merely immature, it may have been more permissive, more willing to allow concentration, collapse, obscuration, and rapid feeding before larger structures settled into the balanced relationships we later came to think of as normal. What we call normal may simply be the long-term outcome of a much wilder opening. This is why the line between black hole formation and galaxy formation becomes so difficult to hold cleanly. Galaxies are not inert containers. They are evolving systems of gas, stars, dust, dark matter, radiation, and feedback. Black holes are not detached beads dropped into them later. They interact, they heat gas, they can stir, expel, regulate, or redirect matter. If one of these black holes gets large enough early enough, then the host is not merely the environment in which it sits. The host becomes, in part, the thing it is helping shape. That may be the deepest shift in perception here. The question is no longer only whether early black holes existed, it is whether, in some systems, they belonged not to the aftermath of galaxy growth, but to its opening architecture. Whether the central concentration came first in the meaningful sense, establishing power before proportion. And once that possibility settles in, another old assumption starts to wobble. We tend to think of observation as a clean act, as though the universe simply presents itself and we record it. Webb reminds us that seeing is more difficult than that. The objects now driving this story were not obvious for most of human history, or even most of astronomy. They were hidden by time, redshift, dust, faintness, and our own technological limits. The black holes may have been ahead of their galaxies. In a quieter way, reality has also always been ahead of us. That is one of the most humbling undercurrents in this whole story. For decades, even when we understood in theory that the universe had an early history full of hidden transitions, our actual view of that era was narrow. We could infer, model, estimate, and argue, but much of the first billion years remained like a coastline seen through thick weather. A few bright beacons came through. Most of the terrain did not. So our narratives about sequence, while grounded and often elegant, were also shaped by what our instruments happened to let through. Webb has not ended that limitation, but it has pushed the fog back far enough to expose how selective our earlier vision was. And when fog lifts, the world does not become simpler. It becomes more detailed, which often means more difficult. That is why these discoveries do not feel like a neat replacement of one theory with another. They feel more like the first honest look at a crowded room. We're seeing enough now to know the old furniture diagram was incomplete, but not enough to pretend every object is fully understood. There are bright early quasars. There are compact red sources that strongly suggest hidden accreting black holes. There are overmassive central engines compared with their hosts. There are systems that seem surprisingly mature in their feeding structures. There are cases whose environments look less crowded than expected, and there are chemically young hosts that make long preparatory histories harder to assume. None of those facts alone settles the cosmic order of operations. Together, they make the old confidence feel too smooth. And the smoothness was always suspicious anyway, because the universe rarely builds everything at the same pace. We see that everywhere, even close to home. Bodies do not mature evenly. Cities do not expand uniformly. Economies do not develop all sectors at once. Forests do not regrow in clean synchrony after fire. Some parts rush ahead, others stall, others remain hidden until the canopy opens. The need for a neat cosmic sequence was partly intellectual convenience. It is easier to teach and easier to picture. First this, then that, then the stable relationship, but gravity is not a lecturer. It does not owe us a tidy order. In fact, the early universe may have favoured imbalance. Dense gas was more abundant. Conditions were more extreme. Short-lived massive stars could transform local environments rapidly. Radiation fields from nearby sources could change whether gas cooled or fragmented. Mergers and inflows could drive matter inward violently. Under those circumstances, it is not hard to imagine certain regions becoming laboratories for concentrated growth, not peaceful places, productive places, in the blunt gravitational sense. If a black hole found itself in the right conditions early enough, the surrounding system might spend the next hundreds of millions of years catching up to something that had already become dominant at the center. That would help explain why ahead is such a useful word here. It has more texture than simply bigger or earlier. A black hole can be ahead in several ways at once. Ahead in mass compared with the stars around it. Ahead in feeding efficiency. Ahead in visibility at some wavelengths, or paradoxically ahead while still hidden behind dust. Ahead in organizational maturity, as if the machinery of accretion has already settled into a powerful mode. Ahead even in causal influence, shaping what the host galaxy will later become. And when you think of it that way, the title stops sounding provocative and starts sounding precise. James Webb revealed black holes forming before massive galaxies, not because it found them existing in pure isolation with nothing around them, but because it found systems where the central black hole seems to have crossed important thresholds before the surrounding galaxy crossed the ones we expected to come first, before the galaxy was massive enough, before it was chemically old enough, before it looked proportionate enough, before it looked finished enough to make the center feel reasonable. That is a very different kind of cosmic surprise than the generic version people often imagine. It is not surprise for spectacle's sake. It is surprise born from sequence failure. And sequence failure always has consequences. If heavy black hole seeds were possible, then the early universe had channels of collapse that were more direct than the familiar stellar route. If sustained super-Eddington growth happened in some systems, then early feeding may have been more aggressive and more stable than earlier models often assumed. If obscured growth was common, then our census of early black holes was missing a hidden majority. If host galaxies could remain compact, dust-rich, or chemically simple, while central black holes surged ahead, then galaxy-black hole coevolution may need to be retold not as a synchronized dance from the very beginning, but as a messy negotiation whose balance emerged later. That point is crucial. The familiar local relationship between galaxies and their black holes may still be real, deep, and profoundly important. Webb is not erasing it. It is showing that this relationship may be a late achievement rather than an early rule, something the universe grew into, not something it started with. There is a quiet elegance in that idea. Order may not have been initial. Order may have been the result. If that sounds abstract, bring it back down into matter. A young galaxy is not a graceful spiral seen in a coffee table photograph. It is gas. It is dust. It is turbulence and light. It is bursts of star formation, violent radiation, inflow, outflow, heat, shadows, chemical change. Somewhere in those conditions, a black hole begins feeding, and the act of feeding is not private. Matter falling inward releases astonishing energy. That energy can alter the gas around it, influencing whether future stars form efficiently, whether material is expelled, whether the host compacts, whether the environment cools or stays stirred up. The black hole is not merely growing inside the galaxy, it is participating in the galaxy's becoming. That is why a black hole getting ahead early matters so much more than its own biography. We are not just asking how one object became large. We are asking whether some of the first galaxies were built around early centers of power that changed their destinies from the inside out. And this is where the story gains a slightly unsettling human echo. Again and again, when we study complex systems, we find that concentration can appear before balance. Cause form, power centralizes, the surrounding structure develops in response. Sometimes it stabilizes into something durable. Sometimes it distorts everything around it. The young cosmos is not a political system, of course, and forcing that analogy too hard would cheapen the science. But the shape of the phenomenon still feels familiar. Central intensity can arrive before distributed maturity. A nucleus can become decisive before the wider body is caught up. That recognition is part of what makes the Webb results so gripping, even for people who do not follow astrophysics closely. Beneath the technical language is a very legible drama. We thought the home made the hearth. Webb is finding cases where the fire may already have been burning hard while the home was still under construction. The more closely you look, The less this feels like a weird corner case and the more it feels like a clue about how beginnings work. Not just cosmic beginnings, but beginnings in general. They are uneven. They lurch. They produce concentrations before distributions. They generate engines before equilibrium. They do not always honor the gentle timelines we invent after the fact. And yet, for all this disorder, Webb is not showing us chaos in the lazy sense. It is showing us processes, physical roots, measurable consequences. The beauty of this moment in astronomy is that wonder and discipline are still working together. The data are strange, but not meaningless. The interpretations are bold, but not reckless. Scientists are not saying, the universe makes no sense. They are saying, it makes sense in ways that may be less sequential, less comfortable, and more inventive than we thought. That distinction keeps the story grounded. It prevents us from sliding into myth. The early universe was not magical, it was physical. Gas collapsed, radiation pushed back, heavy elements accumulated unevenly, dust obscured light, gravity amplified some regions and starved others. Black holes formed, fed, merged, and altered their surroundings. Everything about that is real matter doing real things. The surprise is not that physics failed. The surprise is that physics, given enough density and youth and opportunity, may have produced mature central engines sooner than our intuition was prepared to accept. An intuition, once broken, rarely repairs itself in the same shape. Because after you understand this story, it becomes harder to picture the first galaxies as soft lanterns slowly brightening in an otherwise orderly dark. Some were surely that, but some may have contained something more concentrated from very early on. Compact cores already swallowing matter, already releasing energy, already out of proportion to the visible host, little furnaces inside unfinished rooms, which means the earliest visible light of structure may not always have come from stars spreading gently through a growing galaxy. In some places, the light may have been announcing a central hunger first. That possibility forces us to look more carefully at what a galaxy even is when the universe is this young. In ordinary language, a galaxy sounds like a completed object, as though there were a clear moment when enough stars gather, enough structure appears, and the thing deserves its name. But nature does not care about our categories. At a few 100 million years after the Big Bang, many systems are still assembling, still thick with gas, still compact, still unstable, still becoming. So when we ask whether black holes formed before massive galaxies, we are really asking something sharper. Did some black holes become major actors before their hosts had grown into the large, enriched, proportionate systems we usually imagine? Webb keeps nudging that answer toward yes, at least in some cases. Not yes in the absolute cinematic sense, not a black hole drifting in pure darkness waiting for a galaxy to arrive later like a stage set. The truth is more interesting and much more grounded. The host exists, but it may be small, chemically young, dust-shrouded, or simply not massive enough to make sense of the thing at its center. The black hole is there early enough, large enough, and active enough that the host begins to look like the incomplete context for an already dangerous concentration of gravity. That phrase, dangerous concentration, is worth holding for a moment. Not dangerous to us, not in any everyday sense. Dangerous to the balance of the young system itself. A feeding black hole is not quiet. Matter spiraling inward becomes hot, radiates intensely, and can drive powerful effects into its surroundings. The central engine can ionize gas, stir it, sometimes expel it, sometimes regulate the very star formation that would otherwise help build the host. In that sense, an overachieving black hole is not just an object outpacing its galaxy. It is an object capable of changing the pace at which the galaxy grows around it. So the old relationship between galaxy and black hole may have to be turned around. We often imagine the galaxy as the parent structure, and the black hole as a consequence nested inside it. Yet in these early systems, cause and consequence may overlap. The black hole may be both product and producer, born from the host's gas but then immediately helping decide what the host can become. The tenant becomes part architect. That would help explain why later galaxies settle into those familiar local correlations. Perhaps they did not begin in balance at all. Perhaps balance emerged after long periods of feedback, conflict, fuel exhaustion, mergers, and regulation. Perhaps the nearby universe gives us the ending of the story so cleanly that we forgot beginnings are allowed to be lopsided. There is something almost historical about that. When we study old institutions, empires, or cities, the finished form can make the origin look inevitable. A stable capital makes its chaotic founding easy to underestimate. A mature system hides the improvisation that made it possible. The local universe may be doing something similar to our intuition. We are surrounded by galaxies whose central black holes, while still astonishing, usually fit into a relationship that feels durable. It is easy to project that backward and assume the opening chapters must have carried the same logic in miniature. Webb is revealing that miniature may be the wrong metaphor. The first billion years may not have been a scaled-down version of modern cosmic order. They may have been a period of violent asymmetry, in which some cores formed or grew so efficiently that later harmony had to be built around them. Not a small copy of the present, but a rough forge out of which the present eventually emerged. One reason that matters so much is that it changes the emotional weight of the telescope itself. Webb is often described in terms of distance and sharpness, and both are true, but neither gets at what feels most extraordinary about this moment. We are not merely seeing farther, we are seeing earlier enough to catch reality before its long compromises were finished. We are seeing structures in a state that later time would smooth over. Imagine being able to look at a mountain range before erosion softened its lines, or a language before centuries wore down its grammar, or a city before traffic patterns and habit disguised the logic of its founding. That is the deeper gift of early universe astronomy. It lets us watch things before they become familiar to themselves. And what these black hole results suggest is that familiarity is deceptive. The mature universe tells one story. The young universe may have lived another. This is also why the little red dots continue to loom so large in the imagination of astronomers. They are not visually grand in the way a famous spiral galaxy is grand. They do not greet the eye like monuments. They are compact, obscure, easy to underestimate. But hidden things are often where sequence breaks first show itself. A compact red source at extreme distance is not just visually small, it is informationally dense. It could be dust, it could be stars, it could be a black hole buried inside thick gas, and when multiple lines of evidence keep pointing toward buried black hole activity, those little points of light become a kind of census of hidden acceleration. A census of hidden acceleration. That may be one of the best ways to think about Webb's contribution here. Before, we had some of the loudest survivors, the quasars impossible to ignore. Now we're beginning to glimpse the broader ecology around them, not just the brightest winners, but the concealed growth phase that may have been much more common. That matters because extreme objects often look less mysterious when you finally see the population they came from. A giant tree in a foggy field seems miraculous until the fog lifts enough to reveal a whole forest of younger growth around it. The tree is still remarkable, but now it belongs to a process. And that is exactly what the black hole story needed, a process. The old problem with the earliest giant black holes was that they could feel like singular headaches. Clever theorists could always propose special conditions. Maybe this one grew unusually fast. Maybe that one merged repeatedly. Maybe an especially favorable environment made it possible. All true, perhaps. But once you begin finding many compact early systems likely powered by accreting black holes, the conversation changes from exception management to population dynamics. You start asking not how one miracle happened, but what the early universe was generally allowing. That question does not weaken the mystery. It strengthens it, because a population implies rules. If obscured black hole growth was common, then gas-rich, dust-rich compact systems may have been natural nurseries for central engines. If overmassive ratios show up in some early hosts, then lag between black hole growth and galaxy growth may have been routine in certain conditions. If chemically primitive hosts can still harbour powerful black holes, then large seeds or brutally efficient growth are no longer fringe conveniences. They become working parts of a serious picture. And yet, even here, the most careful interpretation remains open rather than dogmatic. There is not one clean answer waiting at the back of the book. The young universe may have had multiple channels. Some black holes probably did descend from stellar remnants and grew through ordinary, if accelerated, pathways. Some may have benefited from temporary episodes of feeding above the conservative limits astronomers once treated as standard. Some may have begun from unusually heavy seeds. Some may reflect combinations of all of these. Webb may not be forcing one replacement theory. It may be forcing us to abandon the idea that one pathway was ever enough. That complexity is not a flaw in the story, it is what makes it feel alive. Because reality often deepens not by becoming simpler, but by becoming more plural, more than one road, more than one timescale, more than one balance between central growth and host assembly. The temptation to flatten all black holes into a single origin story is understandable. It satisfies the part of the mind that wants one elegant staircase. But the data now whisper something rougher and more honest. There may have been elevators, service ladders, side doors, and trapdoors too. And what joins them is not sameness of mechanism, but sameness of consequence. In system after system, the center can get ahead. Once you understand that, you start noticing how strange the word galaxy becomes in these contexts. It stops meaning a serene island of stars and starts meaning a temporary negotiation between collapse, light, chemistry, and feedback. Something is gathering, something is forming, something is shaping the terms of what comes next, and in that negotiation, a black hole may sometimes become decisive long before the host looks ready to wear the full dignity of the name we later give it. That brings us back to a more personal scale. If you were somehow able to stand inside one of these young systems, nothing about it would feel like the polished astronomical pictures we know from calendars and textbooks. The sky would not contain the familiar richness of a mature stellar civilization. The environment would be rawer, denser, more local in its violence. Gas clouds could dominate, dust could choke visibility, star formation might flash in brief ferocious episodes, and somewhere in that thick interior, beyond what your eyes could ever safely read, a black hole might already be reorganizing the future. Not patiently waiting, already acting. That is the real force of Webb's revelation. It is not merely showing us old objects, it is showing us agency arriving early in the universe. Concentration of influence appearing before the larger structure around it had fully become itself. And once that pressure is visible, the next question becomes unavoidable. If some of these black holes were this early and this advanced, what kind of beginning could possibly have produced them? For a long time, the most intuitive answer began with stars. The early universe makes massive stars quickly. Some of them live fast and die young, and the collapsed remains become black holes. From there, enough gas falls in, enough mergers occur, enough time passes, and the black hole grows. This route is real, and nobody serious needs to deny it. The difficulty is not whether it can happen. The difficulty is whether it can happen fast enough, often enough to explain what Webb is helping us see. That difference matters. A theory can remain correct in one domain and still become insufficient in another. Stellar remnant seeds may well account for many black holes across cosmic history. But some of the early systems now on the table feel like they are asking for something more forceful at the starting line. Not because astronomers want drama, but because the clock is so tight that drama may have been built into the physics. The clock is always the quiet antagonist in this story. When we say a black hole is already enormous a few 100 million years after the Big Bang, those numbers can numb the mind if we're not careful. Hundreds of millions of years sounds abundant in daily language. It is not abundant here. It is an opening interval. If you compress the age of the universe into a human life, these objects are appearing when the cosmos is still in its first breaths of infancy. There has not been time for many leisurely cycles of stellar birth, death, enrichment, cooling, regrouping, and repeated growth unless the process is unusually favorable from the start. So theorists have had to ask, over and over, what counts as favorable enough. One answer is simply that early black holes may have eaten more aggressively than we once treated as normal. The practical feeding limit often discussed in astronomy is not a brick wall. Under some circumstances, a black hole may exceed the conservative pace for periods of time. Not forever, not without consequences, and not in a way that turns the laws of physics into decoration, but enough to matter. If gas is dense, inflow is strong, and geometry cooperates, growth can surge. That is an important possibility because the young universe was not short on fuel. Gas was everywhere. Galaxies were more compact. Interactions were common. Conditions were extreme. In such environments, black holes may have enjoyed phases of feeding that later eras rarely allow so easily. They may have bulked up in bursts, with intervals of ravenous intake that let them leap forward while the host was still trying to define itself. Yet even that may not be the whole answer. Because aggressive feeding still has to start from something, and a very small seed leaves a very large climb. That is why heavy seeds remain so compelling. If some black holes began not from the corpse of an ordinary star but from something much larger, then the later growth no longer has to perform miracles. It still has to be efficient, but the opening disadvantage is reduced. The race begins halfway up the hill. This is where direct collapse returns as more than a speculative curiosity. The idea is physically severe but conceptually simple. A large primordial gas cloud, under the right circumstances, avoids shattering into many separate stars. Instead, it collapses into a massive object and then into a large black hole seed. The details are difficult. Conditions have to suppress fragmentation. Radiation fields may need to keep molecular cooling in check. The collapse must remain coherent enough that the gas does not break into the usual stellar swarm. But if those conditions exist even rarely, the payoff is huge. You skip the slowest steps. In ordinary life, we do not find this kind of shortcut strange. Cities sometimes grow block by block and sometimes leap because a port, a mine, or a railway suddenly concentrates opportunity. Industries sometimes emerge gradually and sometimes take shape around one astonishingly large initial investment. Why should the young universe have offered only one tempo of beginning? Why should gravity, given a richer and denser cosmos, have restricted itself to the most patient route? Webb's black hole results do not prove direct collapse in every early system. That would be far too strong, but they do something almost as important. They make the universe look like the sort of place where direct collapse would make sense. That is a subtle statement, but a powerful one. A theory becomes more believable not only when it is proven directly, but when the broader world starts looking compatible with it. A near-pristine host, an overmassive central engine, signs of hidden growth, mature accretion structures showing up almost indecently early. Each of these makes the idea of heavy seeds feel less like an emergency patch and more like part of the natural menu of possibilities. There is another route too, and it lives somewhere between these pictures. Perhaps some early seeds were modest at first, but were born in environments so rich with inflowing gas that they could sustain exceptional growth almost immediately. Perhaps dense nuclear regions inside compact young galaxies acted like pressure chambers. The host itself, even before becoming large by later standards, may have been perfectly capable of funneling matter inward with shocking efficiency. In that case, the black hole does not need an exotic birth so much as an extraordinarily favourable childhood. That possibility has its own beauty because it refuses the false choice between special seeds and special feeding. The early universe may have offered both: large starting masses in some systems, wildly efficient nourishment in others, repeated mergers adding still more weight where structure built up locally, a genuine ecology of black hole birth and growth, not one pristine mechanism marching across the sky. And once you picture that ecology, the early universe begins to feel less like an empty beginning and more like a dense contest. Gas collapsing into stars, stars burning and exploding, radiation heating nearby clouds, some regions fragmenting, some resisting it, some black holes appearing in ordinary ways and some perhaps emerging through more direct collapse. Matter pouring inward, energy pushing outward. Tiny differences in local conditions producing wildly different futures. In that landscape, it becomes much easier to understand how sequence could break. Because galaxy first, black hole second sounds natural only if the growth of both is smooth and comparable. But if some black holes are born large, or fed at astonishing rates, or hidden inside compact hosts, we underestimate at first glance. Then the center can outstrip the visible whole almost before the whole has introduced itself. By the time we resolve the surrounding galaxy properly, the black hole may already be acting like a mature force. That is one reason the overmassive host ratios feel so disturbing. They are not just measurements, they are evidence of temporal mismatch. The center and the host are not on the same developmental schedule. One of them got there early, and schedule, in a story about cosmic beginnings, is everything. Because once two pieces of a system start running on different clocks, feedback begins to matter. A black hole that gets ahead can alter the gas supply, heat the core, regulate star formation, and change how quickly the host catches up. The mismatch can become self-reinforcing. What began as early advantage becomes architectural influence. The black hole does not merely arrive first in some symbolic sense. It shapes the conditions under which the rest of the structure must grow. That may be the most profound shift hidden inside all the measurements. We are not just discovering that early black holes were larger than expected. We are discovering that in some systems, the center may have been setting terms before the larger body became massive enough to resist or balance it. The future galaxy grows not around a neutral point, but around a pre-existing concentration of gravity and energy. It is difficult not to feel the strangeness of that in human terms. We are used to believing that large systems produce strong centers. Here, at least sometimes, strong centers may have helped produce the large systems. That is not a small correction. It is a reversal of emphasis. And it helps explain why the story still carries uncertainty without losing force. The uncertainty is about root, proportion, frequency, and exact interpretation. The force comes from the repeated shape of the evidence. However we explain each case in detail, Webb keeps showing us early black holes that seem too advanced for the simple, comfortable version of cosmic chronology. They are too heavy, too active, too hidden in ways that imply intense growth, too mature in the machinery around them, or too embedded in hosts that still look chemically young. Different clues, same pressure. The center is ahead. That is the line the data keeps drawing across our intuition, and it changes the meaning of cosmic dawn. We were not just waiting for the first galaxies to turn on like lamps in the dark. In some places, something more concentrated may already have been burning at the core, gathering power before the surrounding structure had fully taken its shape. Once you see that, another possibility starts to emerge. Quiet, but enormous. Perhaps the first massive galaxies were not simply the environments in which giant black holes later appeared. Perhaps, in some cases, they were the long aftermath of black holes that had already begun to matter. That idea sounds radical only because we are so used to imagining galaxies as the main characters and black holes as their dark accessories. But if we strip away habit and look only at process, the hierarchy becomes less obvious. A galaxy is not a single thing. It is a long accumulation of matter and feedback, stars and gas and dust and chemical inheritance, all unfolding inside a larger halo of dark matter. A black hole, by contrast, can become physically tiny, yet dynamically central. It does not have to dominate the entire mass budget to dominate the conditions in a crucial region. It only has to get there early enough. That is what makes the Webb era so fascinating. It is not merely revealing old objects, it is revealing leverage. A central black hole does not need to outweigh its whole galaxy to matter disproportionately. If it begins feeding intensely, the radiation and outflows from the surrounding accretion flow can transform the inner gas. They can heat it, ionize it, stir turbulence, sometimes drive it outward, sometimes redistribute it. All of that feeds back into star formation. Build stars too quickly and the environment changes. Feed the black hole too efficiently and the environment changes differently. Either way, the center is not passive, it becomes a source of decisions. This is the part of the story where the phrase forming before becomes richer than a simple timestamp. We're no longer talking only about whether the black hole existed a little earlier than the surrounding stars. We're talking about functional priority. Did the black hole become an organizing influence before the host galaxy became massive, enriched, and structured in the way we expected? In some of the systems Webb is helping expose, that possibility feels increasingly hard to avoid. And that matters because functional priority is often the real beginning of things. A city technically begins before its skyline, but once a financial center emerges, it starts directing what roads get paved, what land becomes valuable, where labor flows, how the future city arranges itself around concentrated power. In a similar way, an early black hole that gets ahead can stop being just one outcome among many, and start becoming part of the reason the galaxy takes the shape it does. The host is not merely the cradle. It is also the material being negotiated by a force already active at the center. This does not mean black holes built galaxies by themselves. That would be a cartoon, and the actual universe is subtler than that. Dark matter still provides the gravitational scaffolding. Gas still has to cool and collect. Stars still have to form and enrich the medium. Mergers still matter. Cosmic filaments still feed matter into growing systems. What changes is the balance of agency inside the young host. The black hole may join the story earlier, and with more weight, than the older narrative allowed. That earlier involvement may help explain why the local universe looks so orderly by comparison. We tend to take today's relationship between galaxies and their central black holes as evidence that the two grew in lockstep from the start. But another possibility is that they began in mismatch and only later converged. Over billions of years, through feedback, mergers, star formation, gas depletion, and repeated adjustments, the host and the center may have moved toward the correlations we now treat as basic. The neatness around us may be a negotiated piece, not an original condition. If that is true, then Webb is not simply giving us better images of the past, it is showing us the rough draft before the editing. That explains why chemically primitive hosts are so emotionally powerful in this conversation. A low metallicity or near pristine environment tells us the edit has barely begun. There has not been much time for repeated stellar generations to write their residue into the gas. The place still looks close to its starting materials. So if a significant black hole is already there, already feeding, already affecting its surroundings, then the black hole does not feel like the late product of a long galactic biography. It feels like an early event in a place that has scarcely had time to become historical. That is one of the most beautiful and unsettling things Webb has given us. Evidence not just of age, but of uneven age. The universe is not old or young in one way at a time. A single system can contain pieces running on different clocks. A host galaxy can look chemically young while its central black hole looks dynamically mature. A compact red source can look visually modest while hiding a ravenous engine. A distant quasar can look lonely in its environment while still carrying a mass that seems to demand an extravagant backstory. The mismatch is the story. And mismatches are where discovery lives, because mismatch is what tells you your model is too smooth. If all of Webb's early black holes had simply landed where earlier expectations placed them, the telescope would still have been a triumph. We would have learned more, seen farther, refined numbers, and filled in history. But the atmosphere would be different. What gives this topic its grip is that the data keep generating the same unease from multiple directions. The early universe may not have respected the sequence we liked. It may have allowed central engines to rush ahead of the systems around them. That is a stronger and stranger claim than it first appears, because galaxies are the visible architecture of the universe. They are how matter announces stable success over cosmic time. To suggest that black holes in some cases may have gained decisive head starts before their hosts became fully massive is to suggest that concentrated darkness played an organizing role earlier than visible structure. Not absolute darkness, of course. Feeding black holes can be among the brightest things in the universe, but the central object itself remains hidden behind the radiance it generates and the horizon it keeps. A concealed center may have been shaping visible order before visible order looked fully grown. There is something fitting about that. Not mystical, just fitting. So much of science advances by realizing that what is most influential is not always what is easiest to see. Air shapes fire. Invisible microbes shape bodies. Unseen tectonic motion shapes mountains. Dark matter shapes galaxies. And now Webb is making us ask whether black holes, in some early systems, were shaping galaxies before those galaxies looked ready to justify them. The observational difficulty of this cannot be overstated. These objects are unimaginably distant. Their light has travelled for over 13 billion years. It reaches us faint, stretched, partially obscured, sometimes distorted by intervening mass. We read them through spectra, colours, line widths, brightness profiles, and models that must constantly be tested against limited data. This is not the easy frontier of astronomy. It is one of the hardest, which makes the consistency of the pressure even more impressive. Different methods, different objects, different teams, and still the same basic discomfort keeps surfacing. The center is too early. The center is too heavy. The center is too active. The center is too mature. The host seems too slight, too hidden, too chemically young, or too incomplete for the old timing to feel natural. At some point, repeated discomfort becomes a map. Not a final map, not the finished atlas, but enough of one that we can start tracing the outline of a new idea. The first massive galaxies may not have emerged from quiet star building alone, and only later acquired giant black holes in their cores. In at least some cases, both may have grown together in steep imbalance, with the black hole repeatedly taking the lead and the galaxy spending long eras catching up to the consequences. That is the version of the story that gives the title its full weight. James Webb did not merely find ancient black holes, it revealed that the chronology of cosmic structure may have been more top-heavy than we imagined. Before some galaxies became the great massive systems we later recognize, Their centers may already have crossed the threshold into something formidable. And once we accept that possibility, another question follows naturally. If the young universe allowed these early concentrations of power, what did that do to the galaxies that formed around them over the next billions of years? Because a black hole that gets ahead early does not just rewrite the opening chapter, it may leave fingerprints on the whole book. That is where the story widens from origin into consequence. A black hole is easy to treat as a dramatic endpoint, a cosmic object so extreme that once it appears our attention naturally collapses around it. But in the life of a galaxy, a growing black hole is not an ending, it is an intervention. If it begins early enough and feeds hard enough, it changes the terms under which the host continues to develop. The gas that might have become stars does not simply sit there waiting for our categories. It is pushed, heated, ionized, stirred, expelled, compressed, or redirected. A central engine that gets ahead can leave the galaxy that surrounds it, spending ages adjusting to a decision that was made before the galaxy looked finished. That possibility helps explain why the modern universe looks less chaotic than the opening era Webb is exposing. The galaxies around us often carry signs of having negotiated with their centers for a very long time. Some host active black holes today, but many are relatively quiet. Some are still making stars rapidly. Others have become old and subdued. In the larger systems, feedback from central black holes is widely thought to help regulate cooling gas and suppress runaway star formation. The details vary, but the basic principle has become central to galaxy evolution. What happens near the black hole can influence the destiny of the whole galaxy. If that is true now, it may have been even more decisive when everything was young, dense, and less settled. Picture a compact early galaxy full of cold gas, still assembling mass, still chemically immature by later standards. At its center, a black hole starts feeding hard. Radiation pours out from the infalling matter. Winds or jets may emerge depending on the geometry and state of the system. The inner gas responds. Star formation near the center may be altered. Material that would have helped build the bulge might be delayed, redistributed, or blown outward. In some cases, the black hole might choke its own food supply. In others, it might compress gas in certain regions while starving others. The exact outcome depends on details, but the larger point remains. A black hole that arrives early is not just an object the galaxy contains, it is a force the galaxy must live around. That is why the phrase "forming before massive galaxies" is not merely about bragging rights in cosmic chronology. It is about influence preceding completion. If the black hole becomes important before the host becomes massive, then the eventual massive galaxy may partly be the result of that earlier imbalance. The host is not simply delayed in catching up. It may be reshaped by the very thing it is catching up to. This is one of those moments where astrophysics starts to feel unexpectedly intimate. Not because galaxies are secretly like us, but because the underlying logic is recognizable. Early imbalances matter. Things that concentrate first often leave marks on everything that follows. A childhood environment can shape an adult body. A young institution can lock in habits that last for centuries. A city founded around one concentrated advantage can spend generations orbiting that first decision. In a much more literal and less sentimental way, some galaxies may have spent billions of years evolving around central engines that got ahead shockingly early. It also helps us reinterpret what a quasar really represents in the young universe. Popularly, a quasar is often described as a bright beacon from the distant past. True enough. But a quasar is also evidence that matter is falling into a central black hole with extraordinary efficiency. It is a sign that the center is not dormant. It is converting gravity into light. It is altering its surroundings. So when Webb finds early quasars whose feeding structures already look surprisingly mature, the surprise is not only that a black hole existed, the surprise is that a whole system of intake and radiative consequence was already operating with remarkable confidence. That implies history, even when the host does not look old enough to comfortably provide it. Which is why these mature-feeling early systems are so important. Maturity here does not mean serenity. It means organization. It means the machinery of accretion is not just occurring, but occurring in a way that suggests a black hole has already found a workable rhythm with its environment. Not a permanent rhythm, perhaps. Not a stable one by later standards, but a real one, enough to shine, enough to grow, enough to matter. And if the center found that rhythm early, then the host did not have the luxury of evolving in innocence. From that point on, galaxy formation becomes a negotiation with an active nucleus. Every inflow of gas is potentially food for stars and food for the black hole. Every burst of star formation changes the chemistry of the system. Every episode of black hole feeding may answer by changing the gas reservoir again. This is not a clean ladder of steps. It is feedback from the opening act. That word, feedback, can sound technical and bloodless. It is anything but. Feedback is how a system begins talking to itself. It is how one process becomes a condition for another. In galaxies, feedback from black holes can decide whether gas cools and settles or stays hot and diffuse. It can determine whether a compact star-forming core flourishes briefly or is shut down. It can influence the size, shape, and long-term pace of the host. In mature astronomy, black hole feedback has become almost ordinary language. Webb is helping reveal how early it may have entered the conversation. That changes the emotional silhouette of the first galaxies. They stop looking like gentle star-breeding islands that later acquired dark centers, and start looking more like contested interiors, where invisible concentration and visible structure were evolving in tension from the beginning. The stars did not simply light a room. In some systems, they were sharing that room almost immediately with a central power source that could already rewrite the air. There is also a subtle point here about massive galaxies themselves. A galaxy does not become massive just by owning a lot of matter in principle. That matter has to cool, collect, form stars, enrich the medium, settle into structures, survive feedback, and keep drawing in new fuel over time. If a black hole intervenes early, it can alter each of those steps. So when we say black holes may have formed before massive galaxies, we are not only discussing which object existed first, we are discussing which process may have had the earlier hand on the wheel. That makes the title more than a timeline. It becomes a statement about priority of influence. And that is where the whole story begins to loop back on itself beautifully. At the start, the question sounded almost visual. Did Webb find black holes before galaxies? Now the question feels more physical. Did some black holes gain enough mass and activity early enough that they were helping determine whether, when, and how their hosts became massive galaxies at all? That is a much more serious claim. It does not depend on theatrical isolation. It depends on mismatch development and early feedback. It depends on the center getting ahead and staying ahead long enough to matter. If that picture is right, then some of the universe's grandest visible structures were shaped in part by things that became influential before the structures themselves looked complete. The massive galaxies of later time may carry hidden memory of those early asymmetries, not just in the existence of their central black holes, but in the very fact of how their stars formed, how their gas cooled, how their bulges assembled, how their cores compacted, how their later lives were regulated. There is a remarkable humility in that. We look at a mature galaxy, and our eyes go to the visible body, the spread of stars, the beautiful extended form. Yet its history may have been bent very early by something almost point-like at the center, something impossible to see directly, something whose gravity and feeding were already changing the future, while the galaxy still looked young and unresolved. That is a strange lesson, and not one astronomy teaches only here. Very often, what shapes the visible whole is something small, concentrated, and initially hidden. The visible world arrives later, carrying the consequences of a deeper beginning. Still, none of this becomes persuasive unless Webb's evidence continues to hold up under pressure. That is the scientific discipline under the wonder. Astronomers are not free to fall in love with a dramatic sentence and call it truth. The masses of black holes have to be estimated carefully. The properties of host galaxies are hard to infer at these distances. Dust obscuration complicates everything. Spectral lines can be misread if models are too eager. The little red dots may not all be the same kind of object. Chemically primitive hosts require careful interpretation. This is frontier work, and frontier work earns its beauty by surviving skepticism. The remarkable thing is that skepticism has not made the story smaller. So far, it has made it more precise, more careful, yes, but also harder to ignore. Because even after the caveats are applied, the pressure remains. Some black holes in the young cosmos do seem to have become important before their galaxies became what we would comfortably call massive, mature hosts. And if that is true, then we are no longer just looking at ancient objects. We are looking at a universe in which concentrated gravitational power may have started writing the outlines of visible order earlier than we ever expected. The next step is to ask how far that insight really reaches, and whether what Webb has shown us about these earlier systems might change how we understand the entire arc from cosmic dawn to the galaxies around us now. It may seem like a long leap from a handful of distant, difficult objects to the general history of galaxies, but this is exactly how deep science often advances, not by collecting one perfect answer, but by finding a class of observations that makes the old answer feel too narrow. Webb is doing that here. It is not handing us a complete replacement story, polished and final. It is showing that the opening conditions of galaxy formation were probably more varied, more top-heavy, and more structurally uneven than the cleanest older narratives suggested. And that matters all the way down. Because if the early relationship between galaxies and black holes was more mismatched than we thought, then many other assumptions have to be revisited with it. How quickly did the first galaxies enrich themselves with heavy elements? How often did compact gas-rich systems hide active nuclei behind dust? How common were large initial seeds? How often did black hole feedback arrive while the host was still chemically or structurally immature? How much of the mature universe is the settled outcome of those early imbalances rather than the expression of a smooth initial partnership? These are not small edits. They touch the architecture of cosmic history. One of the most elegant consequences is that it may help reconcile two things that once felt awkward together. On the one hand, the nearby universe shows a deep long-term relationship between galaxies and their black holes. On the other hand, the young universe keeps showing us systems where the center appears to have rushed ahead. If you force yourself to choose only one picture, the contradiction feels sharp. But if you allow that the relationship was born out of mismatch and only later matured into correlation, the tension becomes understandable. The peaceful arrangement we see nearby may be the fossilized result of a far more uneven origin. That is a profoundly different way of thinking. It says the mature universe is not the template for the young universe. It is its compromise. Once you say that clearly, many details start snapping into place emotionally. Of course, the earlier structures would be less proportional. Of course, some cores would outrun their hosts. Of course, multiple growth pathways could coexist when gas was abundant and conditions more extreme. Of course, obscured black hole growth might be common in compact, dusty early systems. Of course, chemical youth and dynamic maturity might appear side by side in the same object. The tension remains scientifically difficult, but the universe itself starts to feel more coherent. Not tidy, coherent. There is another reason this matters, and it reaches beyond black holes. Webb's discoveries are reminding us that visibility is not the same as importance. In a young galaxy, the visible starlight may be only part of the story. The hidden nucleus may already matter more than its appearance suggests. That lesson stretches outward into cosmology as a whole. Again and again, what becomes visible later is shaped by what was hidden earlier. Dark matter before galaxies, primordial gas conditions before stars, buried black holes before mature galactic centers. The visible cosmos is not a first draft. It is a later expression of deeper processes that often begin out of sight. That makes Webb's role feel almost philosophical without becoming vague. It is an instrument for catching hidden precedents, for finding out what was already happening before the universe looked the way we expect it to look. And there is something almost tender about that, because it mirrors how understanding works in human life too. We live among finished surfaces and often mistake them for beginnings. We see a mature tree and forget the violence of germination. We see a stable city and forget the brutal luck and concentration that founded it. We see an adult character and forget the early pressures that shaped it. Now we are looking at galaxies and remembering that the polished forms around us are not beginnings either. They are the visible calm that followed a more uneven youth. Still, the scientific caution must stay in view, because that caution is part of what keeps the story beautiful. There are real uncertainties here. Estimating black hole masses in distant systems is hard. Measuring host masses is hard. Separating starlight from active galactic nuclei is hard. Dust complicates interpretation. Sample selection matters. Some little red dots may turn out to have more diverse origins than current headlines imply. A near-pristine host can still hide subtleties. Not every early black hole was necessarily born through the same route, and not every mismatch demands the same explanation. But notice what these uncertainties do not erase. They do not erase the repeated appearance of early black holes that seem too developed for the comfortable version of the timeline. They do not erase the evidence that hidden black hole growth may have been common in compact early systems. They do not erase the possibility that some seeds were much larger than we once preferred to imagine. They do not erase the impression that the first billion years were not an orderly nursery, but a period in which concentrated engines could emerge quickly and decisively. That persistence is what gives the story its credibility. The wonder is surviving contact with caution, which means the question is no longer whether Webb found one or two oddball exceptions. The deeper question is whether we are now watching a broader rebalancing of cosmic history. Not a revolution shouted from rooftops, but a quiet correction spreading outward from difficult data. Black holes may have entered the structural story of galaxies earlier, more forcefully, and through more than one route. In some cases, they may have become major centers of influence before their hosts became the massive systems we later recognize. If so, then the opening hierarchy of the universe was not stars first, centers later. Sometimes the center appears to have surged forward almost immediately. That possibility changes the emotional feeling of distance. It is easy to think of the far universe as remote in a dead way, frozen so completely that it only matters to specialists. But these observations are not dead. They are active arguments reaching us from deep time. They are telling us that the familiar relationship between visible structure and hidden power may have been born under very different terms. The galaxies we love to photograph and classify today may be descendants of a much rougher beginning, one in which the core could become consequential before the body around it looked mature. You can feel the strangeness of that if you imagine history folding. A massive galaxy in the modern universe carries billions of years of stars, dust lanes, orbital order, chemical richness, and the settled gravity of enormous accumulated mass. At its center sits a black hole that now feels like part of the furniture of cosmic reality. But wind the clock backward far enough, and that calm relationship may not dissolve into a smaller calm relationship. It may dissolve into imbalance, into hidden feeding, into compact obscured structures, into giant seeds or furious early accretion, into a time when the center was not a quiet feature of the whole, but a force that could already bend the whole toward its future. That is a very different image than the one most people carry. It is also, I think, the image that makes the title worth telling this way. Because the title is not really about whether black holes won a race against galaxies in some simplistic scoreboard sense. It is about the order of significance, what mattered first, what crossed the threshold into consequence first, what became structurally important before the rest of the system had assembled the visible dignity of mass. And the answer Webb keeps suggesting is that in some corners of cosmic dawn, black holes did. Not everywhere, not by one universal route, not in a way that abolishes galaxies as fundamental structures, but enough to force a different kind of respect for the young universe. It was not only making stars and waiting for complexity to arrive later, in at least some systems. It was already building concentrated central engines that would help decide what complexity became. That is one of the strangest gifts of modern astronomy. The farther back we look, the less the cosmos resembles a simple beginning. It becomes a place of overlapping clocks, hidden accelerations, and structures that do not all wait their turn. The black hole may not be the end of a galactic story. In some cases, it may be among the earliest lines written. And if that is true, then the next time we look at a great galaxy nearby, full of old stars and settled beauty, we may have to see two histories at once, the visible one that took billions of years to unfold, and the invisible one at the center that may have surged ahead long before the galaxy learned how to carry it. That double vision may be the lasting effect of this discovery. Not a new list of exotic objects to memorize, but a changed way of seeing every large galaxy we already know. Once you understand that some black holes may have gained decisive ground before their host became fully massive, the mature universe starts to look less like a collection of finished forms and more like the long cooling of early imbalance. The harmony we see now may be real, but it may also be historical, something achieved after ages of correction rather than something present from the start. This is one reason the Webb era feels so emotionally different from earlier moments in astronomy. The old achievements were extraordinary, but often they expanded the map while leaving the broad intuition intact. Bigger than we thought, older than we thought, more numerous than we thought. Webb is doing some of that too, but with these black holes, it is also disturbing sequence, and sequence is where our confidence tends to hide. We can handle scale shocks. What unsettles us more deeply is finding out that the order of events may have been wrong. That is a subtle kind of awe, but a more enduring one, because once sequence breaks, many familiar questions become richer. What is a galaxy when its core already looks too mature for its visible body? What does young mean if the stars, gas, chemistry, and black hole are not all equally young in the same way? What counts as an origin if multiple roots can lead to early central power? These are not semantic games. They are the natural consequences of looking closely enough that our labels start to fray. And yet, despite all this complexity, the heart of the story remains surprisingly simple. A black hole is getting ahead. That is the line you can hold on to through all the details. Ahead of the expected mass ratio, ahead of the expected growth schedule, ahead of the host's visible maturity, ahead, perhaps, of the galaxy's chemical age, ahead enough that the host no longer looks like the obvious senior partner. Once that becomes visible, the old picture of galaxies patiently assembling first and black holes simply growing within them begins to feel too gentle for the data. The image that keeps returning for me is not of destruction, but of a furnace burning in an unfinished structure. The walls are still going up, the rooms are not fully defined, dust hangs in the air, the surrounding building has not yet become the architecture it will later be. But deep inside, the heat source is already running hotter than seems reasonable. It is already changing the air in every room. By the time the house is complete, the furnace will not feel like an addition. It will feel like something the house was built around. That is close to what Webb is pushing us to consider, and it changes the meaning of cosmic patience. We often speak of the universe as though it had all the time in the world, which in one sense it does. But beginnings are another matter. Beginnings can be ruthless. They can reward any process that gets traction early. In the young cosmos, a region that found a faster route to central collapse or more efficient feeding might not simply be a curiosity. It might establish a long-lived advantage. Billions of years later, the mature galaxy we admire could still be carrying the outcome of that early lead. This is why I think the story resonates beyond astronomy. It reveals a pattern that is larger than its subject. The visible whole does not always arrive before the hidden center of influence. Sometimes the center forms early, accumulates power, and the visible structure grows outward under its terms. Again, this is not metaphor pretending to be science. It is exactly what the observations are pressuring us to consider in physical systems. The metaphor only arrives afterward because the physical truth is already legible to human intuition once it is stated plainly. There is also a deep honesty in how this field is handling the evidence. The claims are strong, but they are not careless. Researchers are still working through selection effects, model uncertainties, and the diversity of early sources. They are debating what fraction of the little red dots truly host accreting black holes. They are refining how black hole masses are inferred and how host galaxies are separated from the central light. They are testing whether direct collapse is needed often, rarely, or only in exceptional corners. This caution is not weakness. It is part of what makes the overall direction convincing. Frontier science sounds most trustworthy when it is willing to leave some doors open. And what remains open here is not whether something strange is happening. It is how many strange roots are contributing to it. Perhaps some early black holes were born from direct collapse in chemically simple, intensely irradiated regions where gas avoided fragmenting into ordinary stars. Perhaps others began as more familiar stellar remnants, but fed in dense, compact environments so effectively that they leapt ahead anyway. Perhaps repeated mergers in some places added sudden mass while inflows kept the engines running. The early universe may have offered not one mechanism, but a set of opportunities. And gravity, given enough gas and youth, took more than one. That possibility may be one of the most mature ideas Webb is forcing us toward. Not the replacement of one overly simple story with a new overly simple story, but the recognition that cosmic dawn was a plural environment, multiple tempos, multiple paths, multiple forms of imbalance. The same general outcome could arise through different combinations of seed size, feeding rate, obscuration, feedback, and host evolution. If so, then what unifies the story is not a single origin mechanism, but a repeated structural truth. Some black holes became major actors while their galaxies were still very much in the process of becoming. The word becoming matters here. A galaxy in the first billion years is not merely smaller than a later galaxy. It is less finished in every sense that our eyes instinctively care about, less chemically worked over, less spatially extended, less dynamically settled, less proportional, and because of that, an early black hole can feel almost indecently advanced by comparison. Not old, exactly, advanced. It has achieved a level of consequence that the rest of the system has not yet visibly matched. That difference between age and consequence is the whole story in miniature. Webb is not showing us elderly objects in young places. It is showing us objects that have become consequential too soon for our old comfort. Consequential in mass, consequential in luminosity, consequential in feedback, consequential in the demands they place on any believable formation history. That is why the title lands if you read it properly. The black holes are not necessarily older than every surrounding star in some absolute personal sense. They are earlier in importance, earlier in architectural force, earlier in the sequence of what becomes decisive. And that may be exactly how the first great cosmic structures learned to take shape. You can feel the humility of that when you remember how recently our species entered this conversation at all. Less than a century ago, black holes were still largely theoretical consequences of general relativity. Strange solutions many physicists were not comfortable treating as fully real. The idea of supermassive black holes anchoring galaxies was not part of everyday human thought. The idea of looking back more than 13 billion years and arguing about whether some of them gained maturity before their hosts became massive would have sounded like delirium. Yet here we are, sitting under an ordinary sky, discussing the sequence in which invisible centers of gravity and visible islands of stars came into being. There is no way to feel normal about that if you let it fully in. And maybe that is part of the ending already taking shape beneath the science. Not a triumphalist ending, certainly. More a quiet recognition that the universe has become stranger without becoming less knowable. Webb is not turning the first galaxies into fantasy. It is making them more physical, more contingent, more uneven, more real. The early cosmos was not a clean prologue. It was a workshop full of concentrated processes, some of which seem to have built black holes into positions of significance before their hosts looked ready to carry them. Once you see that, even the famous galaxies near us become layered differently. Their settled forms no longer feel like the obvious starting point of galactic history. They feel like the eventual surface. Somewhere deep behind them is an earlier phase, compact and gas-rich and dust-veiled, where the center may already have been gathering influence in the dark. And that influence, if it arrived early enough, would have meant that the galaxy was never simply growing by itself. It was always, from surprisingly far back, growing in conversation with something hidden at the core. A conversation with a hidden core is a very different image from the one astronomy once offered the public. The older popular version was cleaner. Galaxies formed out of gas and dark matter, stars lit up, structure accumulated, and much later these elegant systems either acquired or slowly grew the black holes we now find at their centers. There was truth in that picture, but it flattened the timing. It made the center feel secondary. Webb is making that flattening harder to defend. Because the more we learn about these early systems, the more it seems that some galaxies did not first become grand visible structures, and only afterward begin negotiating with their nuclei. The negotiation may have started almost immediately. The host assembled in the presence of a center that was already taking matter, already radiating, already influencing what could happen nearby. In that sense, the first massive galaxies may not have emerged and then discovered black hole feedback as a later complication. Some may have grown into mass under that pressure from the beginning. That idea is easy to say and difficult to absorb. It means that visible cosmic beauty may partly be the outcome of an early argument with something invisible. The argument is physical, not poetic. Gas wants to cool, collapse, and form stars. A feeding black hole releases energy that can interfere with that or redirect it. Dense central regions can channel matter inward efficiently, but they are also the places most vulnerable to being heated, ionized, or blown outward. In some circumstances, black hole activity may suppress star formation. In others, it may compress gas elsewhere and trigger it. The details are not simple, and they need not be. What matters is that once the black hole gets ahead, the host does not simply proceed according to some untouched galactic plan. The plan has changed. That is one reason early black hole growth matters, even if you are not especially interested in black holes themselves. This is not merely a story about one class of exotic object. It is a story about how the universe built major structures. If Webb is right to keep pointing toward black holes that were overgrown, overactive, or overprepared relative to their hosts, then black holes belong much closer to the beginning of galaxy history than popular understanding has usually placed them. They are not late dramatic ornaments. They are part of the scaffolding of consequence. And perhaps that is why the story feels so emotionally disproportionate to the size of the objects involved. The event horizon of even a supermassive black hole is tiny compared with a whole galaxy, yet the galaxy may spend billions of years responding to what happens near that tiny boundary. A small central region can determine the fate of an enormous visible system. That mismatch between physical size and causal importance is one of the recurring signatures of reality. It is also one of the things human intuition consistently underestimates. We like visible spread. We trust breadth. We assume the bigger thing must be the thing in charge. Webb keeps showing us cases where the opposite may have been true very early on. This is also why the term massive galaxy deserves careful feeling, not just technical definition. A massive galaxy is not simply a host with a lot of invisible dark matter in the background. It is a structure that has converted enough gas into stars, built enough central concentration, survived enough dynamical violence, and accumulated enough visible matter to enter a new category of cosmic presence. If a black hole reaches great significance before that threshold is crossed, then the black hole is arriving before the galaxy, in the sense that matters for the title. Before the visible body has become the large, mature system we would instinctively place first in the sequence. That keeps bringing us back to the same realization from different angles. Webb has not merely found black holes that are ancient, it has found black holes that seem early in the stronger sense, early in development relative to their context, early in importance relative to the visible host, early in a way that breaks the soothing order of the old story. And it does so without needing exaggeration. The facts are already enough. A compact red population suggestive of hidden accreting nuclei. Early active black holes only a few 100 million years after the Big Bang. Host galaxies whose inferred masses seem too small to comfortably explain the central engine. Feeding structures that already look organized. Environments not always as crowded as we expected. Chemically primitive systems carrying black holes that appear too mature for long. Ordinary preparatory histories. You can debate each case. You cannot easily ignore the cumulative direction. The cumulative direction is that cosmic dawn may have been less democratic than we imagined. Not politically, of course. Physically. Some regions, some mechanisms, some centers of collapse seem to have concentrated power extremely fast. The early universe may have rewarded local conditions that created dominant cores before broad visible mass had fully spread out around them. In a later, calmer universe, the result looks like balanced co-evolution. In the opening era, it may have looked more like disproportion. There is a starkness to that word that I think belongs here. Disproportion is exactly what makes the evidence feel so vivid, a black hole-to-host mass ratio that seems elevated beyond local expectations, a host that appears too chemically unevolved, a nucleus whose brightness suggests vigorous accretion inside a system that still looks compact and unfinished. These are not just interesting data points, they are disproportions. And disproportion is what tells you a system is not yet settled into the form later generations will mistake for natural. If we are honest, this is often how reality works. The polished arrangement is what remains after long periods of imbalance have been absorbed. The final shape persuades us that the process was balanced all along. Webb is giving us the chance to catch a much earlier stage, before that persuasion becomes irresistible. That is part of what makes the telescope such a historical instrument in the deepest sense. It is not just recording old light, it is recovering unstable order. It is letting us watch the universe before success had become smooth, before the relationships we now teach as standard had finished becoming standard, before giant galaxies and giant black holes had fully settled into the correlations that make the mature cosmos feel understandable. There is a great calmness in recognizing that the universe can be more disorderly at the beginning without being arbitrary. Nothing in this story requires chaos in the loose, mythic sense. There are still rules. Gravity still pulls. Radiation still pushes. Gas still cools or fails to cool depending on its circumstances. Chemistry still records time. Feedback still links one process to another. The strangeness is not that anything could happen. The strangeness is that the allowed range of early outcomes was probably wider than our narratives prepared us for. That wider range is exactly what a good telescope should reveal. Better observation does not always make the world tidier. Sometimes it makes the world more plural. So when people hear that Webb may have revealed black holes forming before massive galaxies, the strongest version of that statement is not a tabloid version. It is not claiming that galaxies were absent or irrelevant. It is claiming something more careful and, in many ways, more profound. In at least some early systems, central black holes may have become significant before their hosts had become massive, chemically mature, or proportionate by the standards we once assumed had to come first. The black hole was not necessarily older than every part of the galaxy. It was ahead in the architecture of consequence. That phrase, architecture of consequence, may be the best way to hold the whole subject together. It keeps us from collapsing into simplistic chronology while preserving the force of what Webb has changed. Galaxies and black holes are not beads on a string, each waiting politely for its turn. They are interacting processes inside the same young environments, but one process can still become decisive first. One can become the structural pressure around which the other grows. And that appears to be what some of these observations are telling us. If that picture continues to strengthen, then the first massive galaxies may have to be reimagined not as the patient cradles of central black holes, but as systems that were, from surprisingly early on, growing around hidden engines already powerful enough to shape their fate. They were not simply birthing the center, they were being built in the presence of the center's hunger. Once that lands, the night sky itself feels subtly different. Not because you can point to any one star and see it. You cannot. The effect is quieter than that. It changes what a galaxy means. It changes what an origin means. It changes what it means for something to come first. And just beneath those changes sits an even deeper shift in perspective. We are no longer studying a universe that politely assembled the visible world and only later introduced its hidden centers. We may be studying a universe where hidden centers were helping write the visible world from the start. That may be the deepest reason this story lingers. It is not just another discovery about distant objects. It rearranges the order in which we imagine reality becoming visible to itself. We like to think the broad shape comes first, and the hidden mechanism later. The landscape first, the engine afterward. Webb is suggesting that in some of the earliest galaxies, the engine may already have been running while the landscape was still forming around it. There is no need to inflate that into something mystical. In fact, the plain physical version is more powerful. Gas falls inward. Gravity concentrates matter. Under certain conditions, the inflow is rapid, dense, and sustained enough for a black hole to grow quickly. Light and radiation from that process push back into the surrounding medium. The host galaxy is still assembling stars, still enriching its gas, still becoming a large visible system. But now it is doing so in the presence of a central source of influence that may already be too large, too active, or too mature for the old sequence to feel comfortable. The resulting galaxy is not simply born and then later modified. It is shaped while being born. That sentence is really the whole thing. A galaxy shaped while being born. Once you accept that possibility, even the distinction between host and occupant begins to blur. The black hole is not only inside the galaxy, it is participating in what the galaxy will count as, and the galaxy is not merely feeding the black hole as a static reservoir. It is changing under the pressures the black hole introduces. The relationship is mutual, but not necessarily symmetrical. In the opening era, the center may have had a way of taking the lead. This is where the story becomes larger than black holes without ever leaving them behind. The discovery is about chronology, yes, but it is also about how structure works at every scale. We often imagine visible size as a sign of causal seniority. The bigger thing must have come first. The broad thing must have shaped the concentrated thing. Yet the universe repeatedly denies that comfort. Small fluctuations in the early cosmos shape later cosmic structure. Invisible dark matter scaffolds the visible galaxies. Tiny atomic transitions write the spectral fingerprints by which we decode the distant past. And now the central engine of some young galaxies appears to have become consequential, before the visible galaxy reached the mass and maturity we expected. The larger lesson is simple. Visibility is late. That line can be misunderstood if it sounds too abstract. So bring it back to the sky. A great galaxy nearby looks serene. Billions of stars, dust lanes, old populations and young populations, long-settled orbits, an enormous visible body. But if its ancestry included an early phase in which a black hole got ahead, then much of what now feels settled may have grown under invisible terms. The visible whole is not the first chapter. It is a later expression of a deeper imbalance that the galaxy eventually learned to live with. That changes the emotional relationship between observer and cosmos. We are not only cataloguing objects, we are uncovering precedents. We are learning that some of the things that matter most begin before they can be seen in their final context. The young universe was not a blank stage waiting for graceful galaxies to take shape and only afterward reveal their central dark secrets. In some places, those secrets were becoming decisive while the stage was still under construction. And that is where James Webb feels less like a telescope in the ordinary sense, and more like an instrument for catching beginnings in the act of being uneven. There is a kind of moral temptation in science communication to smooth discoveries into clarity too early, to take a messy frontier and boil it into a perfect sentence. But this subject resists that for a good reason. The richness lies in the exact way the evidence does not simplify. Some early black holes are bright and obvious, others are obscured, some hosts seem undermassive, some seem chemically primitive, some quasars look more mature in their accretion structures than they should, some environments appear less crowded than expected, some objects may fit direct collapse scenarios more naturally, others may reflect exceptional feeding or repeated mergers. The field is not converging on a single poster image. It is converging on a more plural beginning. Plural beginnings can be harder to narrate, but they are often closer to truth. The first billion years may not have had one canonical path from gas to galaxy to black hole. There may have been several paths, with different regions of the cosmos exploring different combinations of collapse, enrichment, obscuration, feeding, and feedback. Yet across that diversity, one repeated shape keeps appearing. The center can get ahead. That repeating shape is enough to change our mental model of cosmic dawn. The first massive galaxies may not have been the quiet product of star formation unfolding until central black holes naturally caught up. In at least some cases, they may have emerged from an environment where the black hole was already imposing terms, already reorganizing gas, already radiating hard enough to matter, already ahead in the schedule of consequence. That phrase keeps returning because it does the work without overreaching. Schedule of consequence. Not just raw chronology, not just older or younger in some simplistic sense. Consequential earlier, decisive earlier, architecturally present earlier. And when something becomes architecturally present early, its influence extends far beyond the moment of its discovery. Think of what that means for the galaxies we see all around us now. Some may preserve the memory of those early asymmetries in their central bulges, their star formation histories, their gas content, their later quiescence, their correlations with black hole mass. The local relationship between host and center may be the residue of ancient misalignment, a peaceful treaty signed after a rough founding. There is something almost moving in that idea, not because it flatters us, but because it refuses false simplicity. The universe becomes more believable when it becomes less neat. Beginnings should be rough. They should contain accelerations, asymmetries, hidden advantages, local conditions that send some systems racing ahead while others remain diffuse and unformed. Webb is not making the cosmos more dramatic than it is. It is allowing the actual drama of uneven formation to remain visible instead of ironing it flat. And that may be why the most honest emotional response to this discovery is not shock, exactly, but recalibration, a slow internal adjustment, the realization that the great visible structures of the universe did not necessarily lead from the front. Sometimes what led was compact, hidden, and disproportionately powerful. It is worth pausing on how extraordinary that realization is from a human point of view. We are a brief species on a small planet, orbiting an ordinary star in a galaxy that already contains a central black hole of its own. Most of our daily life unfolds at scales where these questions do not seem to matter at all. And yet we have built instruments capable of receiving light from a time when galaxies were still assembling and black holes were already beginning to challenge the order we expected. We are not standing outside the universe judging it from above. We are tiny participants inside it, decoding its earliest asymmetries with tools made of matter that the universe itself produced. That does not make us central, it makes witnessing itself feel more astonishing. Especially because what we are witnessing is not just grandeur, but revision. The cosmos is still teachable. It still contains enough hidden history that a new instrument can force us to redraw our sense of what came first. That is a wonderful thing. It means the universe is not exhausted by familiarity. It means the sky above us is still capable of becoming stranger in careful, evidence-driven ways. And perhaps that is the quiet after-effect this subject leaves behind. Not merely that black holes were early, but that order itself was younger than we thought. The first great galaxies were not always born into balance. Some may have spent their earliest life under the influence of central engines that had already crossed into significance. Massive visible structure came later, proportion came later, chemical maturity came later, calm came later. What arrived early was concentration. What arrived early was hunger. What arrived early, in some systems, was the hidden center. Once that settles in, the modern universe feels less like the obvious form of reality, and more like the long result of deeper beginnings. Every large galaxy becomes, in a faint sense, a solved equation whose rough calculations happened in the dark, and far back in that dark, before the visible architecture fully declared itself, Webb is showing us signs that black holes were already there, not merely waiting inside the story, but helping write it. Helping write it. That may be the line that stays. Because once the evidence is arranged this way, the discovery ceases to feel like a niche correction in astrophysics, and starts to feel like a more general revelation about how reality builds itself. We are so accustomed to the visible world arriving with authority that we forget authority often has a hidden prehistory. The skyline looks like the city, but something older determined where the foundations could hold. The finished organism looks like the story, but early developmental pressures had already narrowed what the organism could become. A galaxy looks like the spread of its stars, but long before that spread became majestic, a central engine may already have begun bending the future inward. That is what Webb is making harder to unsee. Not with one photograph, not with one sensational object, but with a pressure pattern across the young universe. Black holes that seem too massive for their hosts. Compact red systems whose light implies hidden accretion. Nuclei already feeding with startling confidence at epochs when everything should still feel provisional. Hosts that appear chemically young, with too little stellar ash to comfortably support a long, ordinary ancestry. Taken together, these do not scream one theatrical answer. They whisper the same structural unease until it becomes impossible to ignore. The center may have mattered before the galaxy was ready to look like the kind of galaxy we thought had to come first. There is a peculiar calm in that idea once it stops sounding like a headline and starts feeling physical. Of course, the early universe would allow asymmetry. Of course, some concentrations of matter would surge ahead if conditions favored them. Of course, visible order would take time to catch up to invisible processes already underway. The surprise is not that the universe behaved dramatically. The surprise is that our own need for sequence was so gentle. We wanted beginnings to be polite. We wanted stars to gather, galaxies to build, black holes to deepen, and only then for the modern relationship to emerge. Instead, the opening act may have been far more imbalanced. In some places, gas collapsed and fed compact central engines so efficiently that those engines crossed into importance before the host had crossed into visible greatness. In some places, the ash of repeated stellar generations does not appear abundant enough to justify the thing at the center. In some places, the core simply seems too advanced for the body around it. That is the revelation. Not that the cosmos is becoming coherent, but that it may have been willing to let hidden concentration lead. And once hidden concentration leads, everything around it grows differently. That sentence reaches all the way forward, the first massive galaxies, if some of them formed under the influence of black holes already ahead in the schedule of consequence, were not assembling in neutral conditions. They were assembling in conversation with radiation, outflows, heating, turbulence, and altered inflow. They were not merely accumulating matter, they were adjusting to a central fact. The black hole was not waiting for a mature galaxy to give it significance. It may already have had significance while the galaxy was still negotiating how to become massive at all. That is why the later harmony between galaxies and black holes feels so different once you know this story. The modern correlations no longer read as original law. They read as the settled expression of long feedback, Billions of years of negotiation, a relationship that may have begun in the steep mismatch and only gradually found a durable proportion. The mature universe is no less beautiful for that. In some ways it becomes more beautiful because its visible balance now carries the memory of an unruly youth. And that, I think, is the emotional centre of the whole subject. Not black holes as monsters, not galaxies as backdrops, but the universe as something that formed unevenly, with hidden engines sometimes outrunning visible structure, with order emerging later than we like to imagine. Webb is not taking wonder away from the cosmos by making it more technical. It is restoring a deeper kind of wonder by showing that even the first great systems were not born tidy. They had to become coherent. There is also a quiet lesson here about what science is at its best. Science is not the construction of a permanent, flawless picture. It is the disciplined willingness to let reality become less comfortable when the evidence demands it. For years, the broad story of coevolution between galaxies and black holes made sense, and much of it still does. But a good theory is not betrayed by new detail. It is tested by it. Webb has brought back details from deep time that make the older story feel too symmetrical, too calm, too complete too early. So the story changes, not because people want novelty, but because the universe kept too many receipts. And those receipts are made of light older than almost everything we know. Light that left when the cosmos was still in its first long dawn. Light from compact red sources, from young active nuclei, from systems whose chemistry and proportions do not sit easily inside the old intuition. Light that crossed billions of years to tell us that the visible body was not always first. Light that lets a species as local and temporary as ours realize that some of the greatest structures in the sky may have grown around hidden centers already active in the dark. It is difficult to overstate how strange that is without slipping into fake grandeur. So maybe the plainest version is best. We can now look far enough back to catch the universe before it settled into the forms that taught us how to think about it. And in those early glimpses, some black holes seem to arrive not as late consequences of massive galaxies, but as early forces around which massive galaxies may eventually have formed. That does not mean every galaxy began this way. It does not mean every black hole had the same birth. It does not mean uncertainty has vanished. But it does mean something real has shifted. The burden of proof no longer sits only on the idea that black holes can form early. Webb has made early, disproportionate, structurally important black holes a serious part of the landscape. The burden now is to understand how many roads led there, and how much of a later cosmic history was shaped by those roads converging at the center. The center? Again and again the story resolves there, into something small in size, hidden in itself, but immense in consequence. A black hole is the perfect object for this lesson, because it resists our ordinary instincts. You cannot see it directly. Its defining boundary is not a surface in the usual sense. It becomes legible through the matter around it, through what falls in, what heats up, what shines, what is flung back outward. It is known by its effects. And now those effects appear to have entered galactic history so early that the galaxies themselves may, in some cases, be latecomers to a drama already underway. There is a final comfort in that, oddly enough, not comfort in the sense of reducing the mystery, but comfort in the sense of feeling reality become more itself. The universe does not owe us beginnings that look like our textbooks in miniature. It owes us only what actually happened. If that means the first massive galaxies were, in part, the long visible unfolding of black holes that had already seized an early lead, then the cosmos has simply been more inventive than our diagrams were. And what a privilege it is to know that, to sit here now, in an era when an infrared telescope can gather ancient stretched light from the edge of the observable past, and to discover that the earliest visible structures may have been shaped by hidden centers already burning with consequence, to realize that the grand islands of stars we see across the universe may not have come first in the way we assumed, to feel the order of things change slightly in the mind without the sky itself changing at all. That is one of the purest experiences science can give. The ordinary world remains ordinary. Evening comes, cities light up, people sleep under the same stars they always knew, and yet the meaning of those stars has shifted, because somewhere inside the history of galaxies, before the great visible bodies had fully become themselves, black holes may already have been gathering power at the core. not waiting for the universe to grow around them, growing into consequence first. And from that early concentration, slowly, over billions of years, the massive galaxies learned how to appear. So when we say James Webb revealed black holes forming before massive galaxies, the deepest meaning is not that it caught a black hole alone in some empty void and then watched a galaxy arrive afterward like scenery. The deeper meaning is more unsettling and more real. It is that Webb has shown us a young universe in which some black holes appear to have crossed into significance before their hosts became the large, mature, chemically worked, visibly proportionate galaxies we thought should come first. The center was already becoming decisive while the wider structure was still learning how to exist around it. That is a very different kind of beginning. It means the first great galaxies may not always have been patient cradles out of which black holes slowly emerged. In some cases, they may have been systems assembling under the influence of central engines already feeding, already radiating, already heavy enough to distort the old sequence. The black hole was not necessarily the final dark inheritance of a completed galaxy. It may have been part of the pressure that helped decide what kind of galaxy could eventually be completed at all. And once that possibility becomes real, the universe feels younger in a sharper way. Not younger because it was simpler, but younger because it was less settled, less balanced, less finished. A place where chemistry, gravity, radiation, dust, and collapse had not yet negotiated the stable relationships we later mistook for original law. The mature cosmos around us now begins to look like the long result of those negotiations, a peace reached after an unruly opening. That is why this discovery lands so hard. It does not just add another object to the catalogue of the strange, it reaches under one of our basic intuitions and changes it. We tend to believe that the visible whole comes first, and the concentrated hidden force emerges later from within it. Webb is telling us that, in at least some early systems, the hidden force may have gained its lead first. The visible whole may have spent the next billions of years becoming something that could live with that fact. There is no need to make that more dramatic than it already is. The reality is enough. A telescope built by human hands, orbiting in cold darkness, receives stretched ancient light from more than 13 billion years ago. From that light, we infer that some of the earliest black holes were too massive, too active, too mature, or too contextually advanced for the gentler version of cosmic history to hold. We find compact red sources that suggest buried growth. We find hosts that seem too slight. We find environments that do not always fit expectation. We find chemical youth where we expected a longer ancestral record. Piece by piece, a different picture emerges. Not a universe without order, a universe in which order took longer to arrive. And there is something profoundly human in being able to recognize that. We are creatures who live inside finished surfaces. We wake inside structures already built, institutions already old, languages already shaped, worlds that usually conceal their own beginnings. Perhaps that is why this kind of science matters so much. It gives us access not only to distance, but to unfinishedness. It lets us see that the great forms we now take for granted were once unstable. That proportion was not always there, that even galaxies had to become themselves. Webb has carried us close enough to the dawn of structure to watch hierarchy still being decided, close enough to see that stars were not always the whole opening story, close enough to suspect that in some of the first major systems, the black hole was already there at the center, already hungry, already consequential, before the galaxy around it had grown into the mass and maturity we once imagined had to lead the way. That realization does not make the universe colder. It makes it more alive, more contingent, more improvisational in its beginnings, and somehow more intimate too, because the visible calm of the modern sky no longer feels like the natural starting point of reality. It feels like a late achievement, a balanced surface grown over deeper asymmetries. So the next time you picture a galaxy, it may help to picture it twice. Picture the one we know, wide, luminous, resolved, carrying billions of stars in a vast visible body. Then picture the one that came before it, compact, gas-rich, dust-veiled, chemically young, not yet fully proportionate to itself, and somewhere in the core a black hole already feeding hard enough to alter the future. One is the form, the other is the beginning, and James Webb, by reaching far enough back to catch both in the same long history, has shown us something quietly extraordinary. The universe did not always build the visible world first and hide its engines afterward. Sometimes the engine came early. Sometimes the hidden center gathered consequence before the larger structure around it became great. Sometimes black holes were not simply born inside galaxies. Sometimes galaxies grew up around black holes that had already begun to matter. And that may be one of the clearest windows we have ever opened onto what the young universe was really like. Not empty, not orderly, not waiting, but already full of uneven power, with massive galaxies still on the way, and dark centers learning how to lead in the dark.